to FreeBSD. At my employer, the Aerospace Corporation, one of the things that I work on is providing high-performance computing resources to our engineers. And one of the first big resources we built was the Fellowship Computing Cluster, which is a FreeBSD-based cluster. It's got 352 nodes. They're all dual processor or dual socket 1U machines, and about 1,400 cores at this point. And in the process of building this, we built it up on FreeBSD, and we had to port a number of tools over while we did that. So I'm going to talk about the process of porting a few of those tools, some porting peeves that I have, issues that I've run into, and hopefully convince you that porting tools is actually pretty easy, and encourage you to port things yourself, whether HPC tools or other things. So a few tools that we've ported and that I'm going to talk about today are SunGrid Engine, OpenMPI, and Ganglia, which is a cluster monitoring system. So first off, Ganglia. As I said, it's a monitoring system. This is a snapshot of a monitoring interface, not actually the FreeBSD one. This is one of our other Linux clusters. But this is the web GUI. It shows a variety of different status metrics and does a small amount of synthesis of the data, stores most of it in RRD databases. And it's used on a wide array of systems, ranging from monitoring one or two machines up to Planet Lab, which is a multi-site system. It's over 1,000 nodes at 500 sites around the world. It's also used for instance, I know of one large global bank which uses it for monitoring. With Ganglia, what Ganglia does is it reports a number of different metrics about a host. Some of these are fixed, like what operating system is it, or what system architecture. In other cases, they're dynamic, and those are the more interesting ones, things like CPU utilization, memory allocation, potentially temperature, although that's not a standard metric. And most of the built-in providers for things like how many CPUs do you have or whatnot are compiled in, and they just simply report a string or a numeric value. More recent versions of Ganglia also support plugins with, say, a Python interface, although I'm not going to really talk about those in detail. That didn't require any porting. Let's see. So the basic process of porting the metrics over, it's quite simple. First, I'd look at the code on, like say, the Linux side and figure out what do they mean, because in many cases it's obvious. How many CPUs you have is how many CPUs, although there was, interestingly, some disagreement as to what that value should be, as to whether it should be sockets or cores or threads. And we ended up finally going, I think, with threads, but since that's the standard definition, the logical core count. But there was actually some dispute there. So for those things it's easy, but for some of the other metrics, you actually had to go in and read the code and figure out what on earth they were actually extracting. So first you do that, and then my basic process was I'd go and look around on the command line and read man pages and figure out what tool in the system would give me the number that was needed, and then dive into that code, which is the great thing about open source. You say, oh, I can get that out of PS. So how does PS find that, or whatnot? And I'll show some examples of those as we go in. And then you figure that out. You read the man pages, figure out what's actually going on. All that really quite simple. Just requires a little persistence. So a first simple metric is the CPU number function. It's about as easy as it gets. Basically, it returns this strange union structure of it's a generic value type, and in this case it's an integer. There's also floating point numbers, strings, and whatnot in there. So we just go and make a quick sysctl query, get the result, return it. Pretty boring. this implementation is probably gratuitously dynamic, but we don't have that yet. But there it is. A more interesting example is looking at swap. And this one was complicated by one of the porting issues that you'll face, is that we had there are multiple ways to get how much swap is in the system. You can either use the old libkvm interface, which actually goes in and reads kernel memory live, and if you're racing and it's evil and requires privilege, or there was a sysctl interface. The problem for us was that sysctl interface was only in 5, and we were building this cluster on 4 because this was back in 2001. And so we ended up actually supporting both of them because we prefer not to have this KVM socket open in the daemon where anyone could come and read anything. But in some cases, we didn't have a choice. In this case, we just sort of read the swap info man page. Finally figured out. It took a little while to figure out that it's actually pstat, not in the pstat implementation. And swap info is just a name-based behavior change. As I say, we had to support these two methods, and we do runtime selection so that you could have a FreeBSD 4 system, you compile it on there, and then if you upgrade it and the sysctl appeared, you'd use that and you'd stop using privilege. So here's the init function where we do that work. It's sort of I removed things that aren't related to this particular metric. And basically we just check and see if the sysctl is there, and if we do, we create a dummy KVM file descriptor, KVM descriptor, and otherwise we create a real one. There are some things in the libkvm interface which provide the results but actually don't grovel around in the memory and instead use sysctl. So we use those in a few other cases. Then next, here's the swap total actual implementation. And here we just have the little variable that we set and decide which method we're using, and dig up the memory use. One oddity here is that the sysctl and KVM return data in a different way. KVM produces a total, sysctl doesn't. Yeah, total here, so that's why the code's a little different, but it's all quite simple. Let's see. And one additional point to make here actually is you see this part with the version. This actually demonstrates, it's generally good practice to put a version in, but this demonstrates the way that versions actually aren't that useful in an API because, well, if we changed the version in the kernel, the code would break because we'd be compiling against the new version. So it points out that the versioning your interfaces is good, but it's not a panacea. It doesn't solve the whole problem. You still have to avoid changing it because every time you change it, you have to at least recompile your code and possibly redo the actual, or change the way the code works. Another one is the next metric, which is a more difficult set to implement. It's not quite as straightforward. Is memory use. And what makes memory use complicated is that every operating system reports the buckets of memory and how they're allocated differently. So everyone has their own idea of what sort of what ways memory can be used. Just somewhat surprising, but it's how it is. So Ganglia reports these total buffers cached, free, and shared, and expects them to mean exactly what they do in Linux top, which makes it very nice for Linux, but kind of sucks for everyone else who's using Ganglia because their operating system reports something else. For instance, in our top, we report active, inactive, wired cache buffers and free, and on any long-running system, free is always a very small number because we don't waste cycles freeing pages that we don't actually need. Whereas other operating systems might or might not have actually freed them, but account them as free. So you can't actually compare the graph of a FreeBSD node and a Linux node because they don't mean the same thing. which is an interesting challenge. In our case, we picked these. This is the mapping here of what sysctls we use for various things. This one I'm not totally thrilled with, but sort of what we had to deal with. Now on the side, related to this is sort of a general issue when you're importing these types of monitoring tools, is matching of schemas for information. So, as I was saying, we have these different memory use. Well, it also happens in, say, networking code. You would think that, there are some things that are common, like everyone counts how many packets are sent, and how many bytes are sent. But people account for different events within TCP or UDP or NFS. And for instance, there are some Linux NFS metrics that don't map very well into FreeBSD, and we actually haven't ported them because only Linux has support for those metrics on Ganglia. Another interesting one is, if you want to look at disk usage, there are two issues there. There's local disks. So usually you want to report how much disk is free on your local machine. But do you care about reporting memory file systems? And that's an interesting question. That's actually not really resolved in Ganglia. I believe they don't report them at the moment, but you might want to if you're using a large temp FS or something. Other one is they typically go in and they select what file systems are local based on file system type. But there's a question, is a UFS file system on an iSCSI target local? I would say probably in that case, but if you had a shared file system, it might not be, or a shareable file system, like a clustered file system. So there's some interesting issues there where it's not always clear what the exact right thing to do is in these sort of reports. So it can help. I think there are some things that a well-designed monitoring system can do that would help, such as a more flexible metric design, where, say, you might report how much memory you have, and then allow different operating systems to report buckets according to what information they actually have. Ganglia doesn't do that at this point, but I think that would be an interesting model to pursue, and probably more compatible with what's actually there and how the different VM systems match.
You still have to compare different systems. So.
Yeah, that's the trick. I mean, there are some things that you can definitely compare. Like, you could compare how much memory is used for resident sets, but that's not what's compared there. So it's kind of tricky. Trying to figure out how you would compare them. Let's see. Yeah, and another thing is, I think, for the file to make sure that the operating system provides appropriate metadata on file systems. So it'd be nice, arguably, if the mount table listed whether or not a file system type was local or network, and that would help a lot. Rather than what we end up doing now is we hard code a list of either things that are local or things that are not local, and then we do at least have a pseudo FS flag, but for synthetic file systems. But otherwise, we have tricky things there. Unfortunately, as implementers, we don't get to choose the schema, or as porters, we don't usually get to choose what schema is there, so we're forced to shoehorn things in. If you're writing a monitoring system, though, make sure to think about this and don't cause trouble for your porters. And probably a good source of information is to look at the SNMP MIBs, where they at least put a lot of thought and argument into it. They might not be right, but at least they did some work. One other issue we ran into with Ganglia was the IPv4 mapped IPv6 sockets. When Ganglia first brought in IPv6 support, it broke FreeBSD on IPv4. The reason for that is that FreeBSD and I think all the Kame-derived stacks deliberately violate the RFC, and for these IPv6 addresses that map to IPv4 addresses, they require you to explicitly bind both an IPv6 and an IPv4 socket. The reason for this is to ensure that you don't have strange behavior, such as when you, in the standard, if you bind an IPv6 socket, you can receive IPv4 data until something else binds to that IPv4 address. So that's got all sorts of potential security problems and debugging issues. So the Kame stacks ignore that. They say you have to bind to both. The problem is that means the trivial IPv6 port method that a number of people used, which was just use the v4 mapped addresses and only keep one socket, didn't work. So code had to be refactored. In the case of Ganglia, we had a long drawn-out argument, and I finally convinced them that they really needed to switch to a multiple socket model and rewrite the code. And they finally did that. They had to make some changes to the Apache portable runtime to make it work. Despite the fact that this has been the case for many years, it still presents a portability barrier. And it would be really nice if we could either get an RFC approved, an RFC change approved, or consider changing the default. I think the default's well motivated, but it's still an issue. The next system I'm going to talk about is Sun Grid Engine. It's a batch scheduling system and resource manager. It also supports interactive jobs, so you can use it to say, I want to run on a Linux box, and it will give you an interactive shell on the least loaded Linux box. It's one of the leading schedulers, probably one of the two major open source ones, the other one being Torque. So we started porting this. We'd actually tried using OpenPBS, which is the predecessor to Torque. It unfortunately was horribly unstable. It kind of worked at 8 CPUs, but when we went up to a full rack, it just kept falling over. We weren't entirely sure if that was because the FreeBSD port was incomplete or it was buggy. The mailing list seemed to indicate that it was just buggy. Fortunately, Sun bought Grid Engine from another company and released it under open source, just as we were getting fed up with OpenPBS. So we jumped in and did a port. It had already been ported to a wide range of operating systems, perhaps too wide a range of operating systems, as I'll talk about in a little bit. So the first thing we ran into with Grid Engine was getting it to try to build. It has this monstrous, nearly 3,000 line C shell script called AIMK, which has no relation to the one that's in PVM, for extra confusion. And each OS and architecture type had its own set of entries in a case statement. So, for instance, Linux for Linux 2.4 and 2.6 were different. And if you wanted to build on i386, it was called Linux. And if you wanted to build on Alpha Linux, it was A Linux. And I think there might have been an S Linux for Spark or something. There were a whole bunch of them. It was a really weird and erratic. They had a hacked up version. There's also a hacked up version of the X11 C dependency generator. Then a bunch of make files and some autoconf. And then in more recent versions, some Apache ANT invocations, because there are a bunch of Java components in addition to the C. It's quite an arrangement. So we made a number of changes there. Let's see, here we are. Yes. So the first thing we did is we changed things around to improve multiple architecture support, because I really felt that I only wanted i386 at the time, but I wanted it to work on all the architectures. And when FreeBSD added a new one, I didn't want to have to go and copy and paste more code and worry about that, because I wasn't going to have the architecture to test on and whatnot. So we added a single section, simple refactoring stuff. I'll change things so that autoconf was always would run if there wasn't pre-generated output, which is how they had been doing it. They'd always pre-generate output for each and every target. And we came up with a sensible platform naming scheme. It actually was once FreeBSD architecture, but turned out that didn't fit in some places. So we cut it down to FBSD. And Linux has since followed this, so they're now Linux-something instead of the random names that you had to guess what they meant. So we actually overall simplified their build system quite a bit. One thing we haven't ported is the Java build support. It used to be that we worked around it previously by grabbing the binary packages from the courtesy binaries and installing that with the port. Unfortunately, they changed their license, so we really should get the Java stuff going. I don't find the features the Java stuff implements very compelling, though, so I haven't got around to it. There's a GUI installer, but why? It's a cluster tool. Another issue we ran into was they had all these portability defines. The code was quite old. It's, I think, 15 or 20 years old. And it was ported to a number of strange platforms such as Craze, Unix, which had 64-bit ints and caused all manner of fun and all manner of weirdness in POSIX, actually. So it predated C99 and all the standard types in C99, so there are own type defs floating around. They also have these weird format macros where you have to tell it what type all of your variables are. So we had to find all of those and add them in. I tried to get them to simplify the code and use standard things, but they still wanted to keep support for ancient, obsolete operating systems, so I haven't won that one yet. There's also in SunGrid Engine, just like Ganglia, there's a whole bunch of host metrics. Because the scheduler needs to know what the load is and what resources are available on different systems, so it can decide which one to dispatch a job to. Pretty much the same as porting Ganglia, so I'm not the Ganglia one, so I'm not going to talk about that in great detail. One thing that was kind of a pain is they were scattered all over the system, so I basically ended up grepping for Linux in the system and finding all the cases where it was where there was something Linux specific, and figured that probably meant there was a metric I had to deal with. And it looks like that's what the NetBSD and Darwin people just grepped for FreeBSD in their port. So one thing that was interesting that had to be ported is they have a system called the Portable Data Collector, which is basically their way of identifying all the processes in a job. This is useful because you want to account for everything that's being done, and a job might spawn off a whole bunch of processes and do different things, or different threads that you need to account for. And to track all of that, they chose an interesting approach, where they take a supplemental group and they generate one that's not used for any permissions, that on a per job basis, and they stuff that into the processes group list. And so they then, when they want to find out all the processes that are in a job, either to signal them or to collect data about them, they walk the process table and look for processes that have that group. Since non-root users can't drop groups, that works. So it's a clever trick, and it was a little fun to port. But it would be a lot easier if we just had IRIX job IDs, which allow you to both do resource to find out the resources used by the job, as well as signaling everything in the job, so you can kill them off. And that would have simplified things quite a bit. But we got it basically worked out.
It's actually got contracts that do kind of the same thing.
Contracts, yeah, they're not quite the same, but they're similar. In IRIX, they're sort of an ephemeral thing. You create a job and it runs to completion and then it disappears. So one of the things on my eventual to-do list is to switch away from the Linux version to a sysctl, or the KVM-based code to a sysctl-based code, now that we finally have this stuff available. That'll probably take some time because we're going to need to support old versions of FreeBSD for at least a while. And I don't think there's a release version of 6 that has the sysctls in it. Another aside of portability issues in sort of a peeve is in signal handling. I think the quote at the bottom really sums up the situation. The basic issue is there are too darn many ways to specify signal handlers, many of which are not at all standard. So we ran into problems where SGE was using System 5 SIGSET, which for us it's trivial. We can just change that to signal because the BSD signal, as opposed to the System 5 signal, acts exactly like SIGSET. But that was sort of unsatisfying. I didn't want to go in and if-def everything. I did talk at one point into switching all the handlers to use SIG action. But SIG action is a pain. It requires 4 or 5 lines of code to set a handler because you have to set up a structure for each thing. So they did that, and then they went and quickly switched back to, when they added new ones, they just sort of switched back. So what we really need to do is add the POSIX versions. Unfortunately, there is code in NetBSD, and it's pretty trivial. It just wraps SIG action anyway. So that's something we probably need to import into FreeBSD to ease portability. The next thing I'm going to talk about very briefly is OpenMPI. OpenMPI is a leading implementation of the message passing interface, which from the name unsurprisingly is a system for writing message-based parallel applications. So you have a bunch of processes and they send each other messages. It hides the details of the network interface. So it could be that it's a TCP/IP, which is what our cluster uses, or it can be using InfiniBand or some proprietary messaging system that lets you send gigantic messages through a proprietary fabric. There's the other main implementation at this point is MPitch, but there are a whole bunch of different implementations. OpenMPI is based on LAMMPI, but also with another number of things. One nice thing about OpenMPI is that it's, well, it shares a bunch of older code. It was completely refactored and it's very modern. So it's actually quite modular. It's definitely one of the easiest ports. It's got an amazing array of AutoCount scripts, kilobytes and kilobytes of them, to put all the modules together and figure out what things you support on your operating system and whatnot. And this is actually a case where, because these people have been writing MPI implementations for years and porting them from platform to platform to platform, many of which were one-offs, because they were working at supercomputing centers where they bought one giant system with thousands of GPUs, and then nobody ever bought another one because somebody else came out with something better next year. So the people writing this knew that they were going to have to deal with that. You know, right now, Linux is in ascendance, but in the HPC world, but you know, they don't really believe that that's likely to be the case forever. Things will change one way or another. And so the code is very portable, which was made it nice. Basically, the only thing we had to do is add backtrace and backtrace symbols calls, which glibc has, and they expected to be there. Fortunately, there was already a libexec.info port, which at least on i386 and AMD64 does the right thing. So we used that. One part that we haven't ported is a system called the Portable Linux Processor Affinity, sort of a side project, but for doing CPU set type manipulation. The reason they actually wrote that instead of using a CPU set type API is to deal with an interesting eccentricity of the Linux implementation. It took quite a while for this code to get into Linux, and in the meantime, I believe both SUSE and Red Hat shipped versions which were not were not compatible with each other in AVI. They used the same syscall number, but different interface, and were different than what actually went into mainline. So they wanted code that would run on any Linux, on any 2.6 Linux, and there was no way to know what version of the syscall was there. So they actually figured out some convoluted set of arguments of different calls you could make to the CPU set function to figure out what the ABI was based on the errors that came back. And so they have this runtime probe where they figure out how they're going to, what the calling convention is, and then use it. So we should actually port to the library because it would be useful. But fortunately for us, it would be really easy because we only have one version. And actually, PLPA has actually been replaced by a new project whose name I can't remember. It's in the paper. It combined PLPA and a project called libtopology. So it both does CPU binding, and provides information on memory topology and hierarchy. So it says, you know, these CPUs, so it can tell you what cache sharing is going on, both on and off chip. So that's actually pretty neat. And in theory, we should be able to port that because we also have an XML output of the CPU hierarchy. One little aside on something that doesn't work quite right in FreeBSD is over on the port side, we really want to be able to support multiple MPI implementations. And actually, ideally, multiple copies of the same MPI implementation, because MPI uses a compiler wrapper to do most of its work, because every different MPI implementation would have a slightly different set of library names and whatnot and header files. So the community convention was to have an MPI-CC and an MPI-C++, an MPI-F77 or whatnot program that you used instead of the compiler. And then you would compile different versions for different compilers, because in the HPC world, you'll often find that you need that one compiler is really good at something and another one's really good at something else. And historically, you've not been able to link things between them, so you had to have different sets. In ports right now, we don't really handle that case very well. So we have some ports that do a decent job, like the GCC ports can all be installed, all the different versions can be installed at once. But in MPI, we have kind of a weird setup. The LAM port is installed in prefix, so prefix bin, prefix lib. The mpich2 port, I think I say here that it's installed in prefix mpich2, but I think it's actually been moved, and I think it's just going into prefix now. And I've been putting OpenMPI in, actually prefix MPI, OpenMPI, not MPI mpich2 as it says here. To be nice if we had more consistent locations and if we allowed them to all be installed at once. And figured out a good way to handle that. I kind of think if somebody's looking for a little project, something like the Java VM wrapper would be a really cool solution. We could have an MPI wrapper, which would be handy, but we're not there yet. So a general summary of issues we've ran into importing things. First of all, we've had these schema conflict issues. These are pretty hard to resolve overall. But I think the big thing is to try to encourage developers of monitoring systems to either pick things that are sufficiently simple that everyone actually has them, or to push on them to do things that are flexible so that different operating systems can report different types, can report the data they actually have, and the things that are actually relevant, despite the fact that might make you have to make apples and oranges comparisons. The next one that we ran into was this IPv6 socket behavior. I think that's a tough one. I mean, really, all the code everybody's code should be refactored to use a multiple socket version and use select or pull or whatever. But the problem with the current code is that means that you can't have a trivial application, trivial single socket application. And get both V6 and V4 support. The next sort of issue is, in many cases with these tools, they have a very long history, and as a result, they have very weird build systems. Sometimes you're lucky and you get something like OpenMPI, which has a nice modern build system by people who actually know AutoConf, so it's not horrid. And in other cases, you get a mess like GridEngine. I mean, we spent, I think, probably a week figuring out how to build it, and ended up having to write a port just to drive it, just so we could have a repeatable build, because it took 6 or 8 steps to get anything done. You had to run different commands and whatnot. Another issue there is with these long history of these programs, there's often not, they're not taking advantage of modern data, of the modern C99 data types or POSIX data types. So you end up with weird differences between operating systems, and have to sort of patch around that with strange definitions. It's also a general case of a lack of good interfaces to some data. For instance, anytime you're going in and using libkvm, and it's actually going in and digging around in the memory, that means we don't have a good interface, because live kernel memory is not a good interface. So that's an issue. I think we're actually making good progress there. We keep adding more and more CTL-based interfaces to get interesting data about processes or or memory use or whatnot. But it's sort of slow. And one area if people are looking to help out and make things better would be to look at what the LSOF author needs. That's one of the constant issues where every time we change anything in the kernel, in terms of file handles or sockets or whatnot, it breaks LSOF because it's groveling around in stuff that no process has any business doing. As a result, that irritates the author and it irritates the user. So that's somewhere where people really ought to be thinking about better interfaces. One word of warning there, if you do it, make sure they are in fact good interfaces, because we're often stuck with them forever. Once we have a syscall, we have that syscall virtually forever. Really don't like to remove or change them. And final one here is the signal handler setup. I think we just need to copy NetBSD's code and port over the POSIX style, the older System 5 style interfaces rather. And actually, one final thing, we really need this libexec.info functionality. It's being increasingly used in more and more places, and unfortunately, that's all architecture-dependent code because it depends on the calling convention of the particular system. But we really could use that. It'd be really nice if we had that in libc. I think Linux did the right thing by putting that in glibc. So first, some more. So I'll finish up here with some more tools to port, suggestions for other people to do, or things that are on my eventual to-do list. I think the Portable Linux Processor Affinity API and its follow-on project would be an excellent thing to port. It should really help people out who are doing CPU binding and that sort of thing. Another is PAPI-based analysis tools. I know GNN's been working on some of this stuff, making these available. These are hardware program counter hardware CPU counter tools, and they allow you to probe different things. It's actually a case where we have a real potential to be a big win for FreeBSD because the original PAPI stuff was developed for Linux over a decade ago, and the high-performance computing community uses it all the time, but it's not in mainline Linux because Linux doesn't like it. So it's actually in FreeBSD by default. So from that perspective, I think that getting more of those tools available and getting them ported would really make us attractive. Another thing for people to look at is the Eclipse Parallel Toolkit tools platform. It adds the ability to do parallel debugging. It's actually based on some of the libraries in OpenMPI for going out and starting jobs and whatnot. And that would be, if somebody's interested, that would probably be a pretty neat project, and potentially could be quite valuable to get that into ports and make debugging of distributed applications easier. And a final bonus one would be something like the ROX cluster framework. It's originally a Linux cluster framework that allows you set up a front end and then you just boot nodes and they hexi boot and get installed. It's fairly nice. I don't agree with all their design choices, but it's actually pretty decent, and it's widely used. And they actually recently added Solaris support. The reason they did that was that they wanted to use thumpers, the X4500s from Sun, running ZFS as NAS devices. And so they built a nice ZFS management framework so they can automatically blow the system away and deploy on it. Their general rule is they like to start with the null set. So they just wipe out a box, throw their own stuff on it. So since they've done all that refactoring, we could potentially add FreeBSD support. They've refactored the package API, so it uses the native packaging system in either the Red Hat packaging system or the Sun packaging system, and that sort of thing. So it'd be a pretty big effort, but it might well be worthwhile. Could really get us a foothold into a number of environments. So a few conclusions. So we've ported a number of tools. In addition to the ones I talked about, we've ported, at one point had a Globus port, which is one of the early grid computing tools. We may actually get that back now that they've returned to their roots and are writing highly interoperable things for fast data transport, and things for starting jobs, and they've sort of abandoned the Java side of things and left that to the web services community. We've also ported little things like the PSSH program and for parallel SSH to run commands, that sort of thing. There are a number of portability challenges, both in terms of general issues like schemas and schema mismatches and that sort of thing, as well as some FreeBSD issues where we're just, in some cases, too different. And so it's useful to look out for those sorts of things and try to fix them so that we can be a more attractive platform and an easier platform for new users to move on to. So I think that's very important. We also, with things like PAPI support in base, have some potential to grab some market share. So I think that can be very useful. So I really encourage you, if you're inspired, to go out and get some more things ported. Make FreeBSD or your BSD of choice a better place to work by getting more tools available. So I would be happy to take any questions. George?
Actually, I just have a follow-up comment to the PAPI library.
Yeah.
The ports maintainer has just committed support for modern Nehalem processors, which we worked on recently. And the other interesting thing there is that the PAPI authors themselves are doing some restructuring of the library, so we're going to try and follow that. But that's probably going to mean I'll need a little more help. So people who want to work with that should email me. I'm GNN, so I'm easy to find. But the latest port actually has support for everything up through the latest Nehalem.
Cool. Anyone else? Well, thank you all for coming.